Okay, let's continue first order system with another example. Um, okay, let's say we have a system's 1 over s plus 2, right? So we know that based on my previous lecture, okay, the first step we have to determine what's the inputs. Let's say the input is step inputs 1 over s, right? Okay, we know that yt, right? Yt is from here, it is 1, 2 minus e to the minus 2t, right? If you use a partial fractions, you will solve this, you get this, okay? From this is our y of s, 1 over s, s plus 2. Okay, we got this. So once we have this, we know that our final state is half, even though the input is 1 of s, the final state response is half, because if this term here becomes this infinity, this term here becomes 0, right? As t approach infinity. So this is our final state, right? Okay, let's try another one. So let's say we have a system's step input just 1 s plus 10, right? So then we have y of s, 1 s plus 10, right? Then in time domain we'll have 1 over 10 minus e to the minus 10t, right? Same things. If this term here becomes 0 and t approach infinity, 0, so the output, the final state is 1 over 10. This is our final state, right? Okay, if we want to the final state to be some values, or maybe in this case equal to 1 instead of 1 over 10, we could increase the inputs to be 10 over s. That means instead of input 1 over s, we got the output 1 over 10, right? So we input the input is 10 over s, then this 10 of s and of s plus 10, right? Okay, so that makes our system becomes this is 10 over 10, right? This is 1 minus 1/10 e to the minus 10t, right? So this term becomes 0 and t approach infinity. That is our final state. So the input will actually influence the output steady state, okay? Because we can't change the systems, we can change the inputs. If we can change the system, we will change the systems, right? If we can't change, we can actually change the inputs so that we can achieve certain desired steady state output, right? Okay, meaning that if we were to calculate the three parameters, right, the first order parameters from systems S plus 2, okay, then we have one of S plus 2, right? Okay, then we Laplace inverse Laplace y of S. We got y of t. That's y of t. We have minus half e to the minus 2t. Okay. So based on this, we know that the output steady state is half, right? Half. Even though the input is the same one of S, but due to the difference of the transfer functions, system transfer functions, the output will reduce to half, right? So if we draw this, the response here, y of t, t0, okay. Then this is our response. This yt half minus half e to the minus 2t, right? So we have to find the same parameters, right? The same parameters again at 6.3% of this. Instead of from 1, it is 6.3%, 0.632 divided by 2, right? Because this is half. Same things here, 0.1, because we know that the output here is 0.5. So 0.1, so you have to divide by 2, 0.9 divided by 2, 0.98, settling time is ds, t2, t1, tau, right? It's tau. So everything has to be divided by 2 because this is the percentage of the response according to its final state, right? So in this case, we have to calculate the same thing. We can use the same method to calculate, but the value of this have to be, you know, divide by half because of the output is half, right? So I'll just show you how to find the tau in this case. So this is y tau. This yt is equal to half minus half e to the minus 2t, right? So at this point, we have e to the minus 2t, the 0.632 divided by 2, right? Okay, then if you calculate this, you solve this, t, which is, in this case is tau, it's it's 0.32. Okay. 0.5. Okay. So that's t equal to ln is 0.368. I'm mistaken. 0.368. So it is just 1 second. Okay. So you can calculate the same parameters using the same method I showed you earlier, right? So that's in this case our tau is 1 second. Okay. Okay, we'll continue another example after this.